So in this video, I'll talk about latent growth modeling with 3D estimated time points. So in most latent growth models, we don't freely estimate the loadings of the slope. We set the loadings of the slope to values corresponding to the hypothesized growth trajectory. So in a linear latent growth model, you would, for example, put the loadings of the slope at 0, 1, 2, 3, 4. And it's also common in nonlinear models to hypothesize specific growth trajectories, such as quadratic, cubic. However, there are situations that the linear model does not fit well to the data, and pre-specified nonlinear trajectories such as quadratic or cubic don't fit the data either. So it may be necessary to freely estimate some of the loadings. So if you freely estimate the loading, you are allowing the data to tell you which growth trajectory best fits the data. So this is how a latent growth model with freely estimated loadings would work. You can't do this if you only have 3 measurement occasions because the model wouldn't be identified. But here you have 5. You are able to freely estimate some of the loadings. You can't freely estimate all of them because the model wouldn't be identified. So you always need to set at least 2 loadings. You set the one loading to 0, which will define what the intercept is, and set one loading to 1. And after that, this can be freely estimated. So here, let's say the third loading is freely estimated to be 1.3. That means that the growth from kindergarten to spring is 1, right? It's a reference amount. And then if this third load is 1.3, that means that the growth between kindergarten and first grade was 30% of what the growth was between kindergarten and fall kindergarten and spring kindergarten. Another option is to set the first loading to 0, the last loading to 1, which is saying that the growth between fall kindergarten and spring 5th grade is 100% of the growth, and the growth that happens in between are proportions. So let's say here, if the spring kindergarten loading turned out to be 0.3, this means that from the 100% of growth that happens from fall kindergarten to spring 5th grade, 30% happens between fall kindergarten and spring kindergarten. Now, there are some situations where individuals have different time points. It could be different ages or different times that they are measured, resulting in a data set with heterogeneous measurement time. So an example is a study with 3 measurement occasions, fall, spring, and summer, in early childhood centers. So children who have age varying from 0 to 60 months. So these are some distributions here that may occur when you have variability in measurement occasions. So uniform would be when you have some individuals at about all time points or ages. You could have moderate skewed, extremely skewed most people are the same time point or same age, but there are some that are more, right? You can observe of these in a data collection. Now, when you have heterogeneity, you need to define what 0 means, right? So in my example of a data collection at early childhood centers, if you don't center the data, 0 would mean a child that's a newborn, right? And you may not want that. You may not want the intercept to be the status of, I don't know, reading achievement when the child is a newborn baby, right? So you have options for centering to change the interpretation of the intercept. Okay, those options are center on the entire sample at a common age time, center an entire sample at overall mean of time, center each person at a certain time for the person, or center each person at the individual mean time. And I will go through these and how the intercept varies. So if you center at a common age time, for example, in the study of children in early childhood centers, if I center at age 3, like 36 months, I would take the original age of the children and subtract 36, which would make the zero be a child at age 3. Therefore, the mean of the intercept is the expected value of the outcome at that age, which is age 3, right? So that would define the interpretation of the intercept with respect to the status of the child at age 3. Another option is to center at the overall mean age or time. So in the study of early childhood children, if I took the mean of the ages for all participants of the study and subtracted from the original age, that would create an intercept, a mean of the intercept that is the expected value of the outcome at the mean age. Um, Now you can center at the individual time. So let's say in my uh, study of early childhood education, if I take the if the individuals, if the children receive an intervention at some point and they have a different ages at that intervention, right? So I can center at the age they were when they received the intervention, whatever age that was for each person. Therefore, the intercept would be their mean at the time they received the intervention. Um, and you can center at the individual mean time. So, like, for example, if you offer an intervention, you can take the mean age at the time of the intervention and then use that for centering. And the mean of the intercept becomes the expected value at the time when the individual age is equal to the mean age. Okay. Now, centering will not affect model fit because those are mathematically equivalent. Um, Therefore, it's possible to convert from parameters with one type of centering to others. So this is how you do it. So if you have, let's say, original scale of time, uh, you switch to another scale of time, uh, and the the new scale, is a function of this other scale divided by k. Therefore, you can use that k constant to obtain the original parameters. So the intercept will not change, uh, but the the individual intercept, but the slopes can be divided by k